it's out in the field, what do we call it? Stream. So if you're describing to somebody what stream is, what would you describe to them? Running water. Okay, flow of water. Like, do you have in your mind that a stream is a particular size?
Yeah.
Like how? And narrow?
Shallow.
And shallow. So if I said we're going to a stream, you would assume you could walk across it, right? Maybe even jump across it.
Yes.
What would you call something that's a little bit bigger?
Creek.
Creek, river, right? In geology, a stream, those are all streams. So a stream is a channelized flow of water. It doesn't matter if it is an inch wide, 10 inches wide, 10 feet wide, or a mile wide or more. It doesn't matter. A stream is any channelized flow of water. Now most of the time we recognize this as the shape, right? Kind of a windy road, because most streams are kind of windy. We call them meandering streams. Because what does it mean to meander? If someone says I'm going to meander about, what does that mean?
Go back and forth.
Wander.
Well, they're just going to kind of wander around, not particularly any mean of getting from point A to point B quicker, right? They're just going to kind of do it as they wish. Well, that's kind of how streams do it, but streams have a real purpose for their meander. Sometimes you have a purpose for meandering, right? You just feel like walking, and you don't really have a particular desire to get to any place, you just want to walk. Streams, of course, do have a particular direction. Where are all streams headed? The ocean, for the most part, right? Can you think of a place where maybe a stream doesn't ever reach the ocean? If it reaches a lake, like what? An example.
Great Lakes.
The Great Lakes. So the Great Lakes, do they ever enter into the ocean at all?
Yeah, 2 places. Hudson.
Yeah, they do. They enter in 2 places. Now, of course, some of that we connected them, didn't we?
Yeah.
The Erie Canal.
Yeah, we've got the Erie Canal and such things. So we've kind of helped that out. But is there any lakes in the world where water goes in, doesn't come out?
Dead Sea.
Dead Sea's one. How do you know the Dead Sea has water come in but not come out?
Lowest point in the world. It's below sea level.
It's below sea level. So anything that comes into that lake is going to be going downhill. How's it going to get out?
Evaporation.
Right, pretty much the only way out for that water is evaporation, right? It can't flow out because it's at the bottom. The other way that we can know that, so what is it about the Dead Sea? Okay, so the bottom on land that we have, it's the lowest point below sea level. What's another thing about the Dead Sea that's so unique? Yeah, it has a lot of salt. How'd the salt get there?
Runoff.
It's runoff. Remember, we talked about weathering. What's one of the products that we have for weathering?
Salt.
What do we call that? Ions in solution. So we've got ions in solution, and they're going to get carried to the stream, or by the streams. Now, if you go drink salt for stream water, now I wouldn't recommend necessarily just scooping up a bit and drinking it, at least not without purifying it. But what, is it going to take salty if you go to any stream? No, but there's still ions in solution in it, right? But when they get to a lake, like the Dead Sea, do those ions ever come out? No, the water comes out, right, by evaporation, but it does not take the ions with it. So they're kind of stuck in there, right? So we could say that any salt lake would be a terminal lake, right? Can you think of another terminal lake other than the Dead Sea?
Salt Lake City. Great Salt Lake.
Great Salt Lake. In fact, the Great Salt Lake is just a tiny remnant of what used to be this huge lake called Lake Bonneville. And it used to cover almost all of Utah, almost all of, in a bit of Colorado, a bit of Arizona. There's a huge area. Everybody heard of the Bonneville Salt Flats. I think I might have mentioned it to you in the past. Bonneville Salt Flats are, in fact, part of the seabed of Lake Bonneville a long time ago. So most of our streams head to the ocean. Some don't make it there. Now, not all molecules of water are going to make it directly from their source to the ocean right away, right? They might end up in a lake for a while. But they're flowing, most lakes, there's an inflow and an outflow. So we go back to meandering. Why do streams meander? Why don't they just go?
The easiest way through.
One of these distance.
Yeah, they're always going to look for the easiest way. Right? If you have two paths to choose from, you're going to the hard one or the easy one. Most of the time, you're going to choose the easy one, unless there's a particular reason for them choosing the hard one, right? So streams are affected, their shape, their speed, by a number of factors that are in the hole, in the drainage basin, in the area that we're looking at now. Some streams have a huge drainage basin, like Mississippi River. Mississippi River drains how much of the United States?
90% of it.
A good portion of it, right? It covers almost everything. It's everything west of, what's this? What's in the, what? The Appalachian Mountains on this side. What's over here?
Rocky Mountain.
Rocky Mountains. And look at us. We're kind of separated. Except for the very northern part of Texas. We have our own series of rivers. Because we always do that, don't we? Texas is special that way, right? We have our own electronic grid. We've got a lot of things that are special. So we've got this big, huge area that's drained by one river. So what would you expect when we get towards the end of the Mississippi River? What would you expect its size to be? Huge, right? If we start back here, would you expect it to be big back here? No. So every time you have two streams meet, the water, the size of the stream is going to increase. Well, it depends on how much water you're putting together. So if you've got two big streams, you're going to get a really big stream. If you have two small ones, you'll have a medium-sized one. Okay, so there are a series of factors. Okay, one is velocity. This is affecting stream erosion and deposition. So what did we say erosion was? Remember we said that oftentimes weathering, we consider erosion to be the same thing as weathering, but erosion isn't? Right, it involves transportation. Erosion involves transportation. What happens after weathering, before deposition, is erosion, where the material is being transported. So velocity is going to affect how much sediment, what type of sediment is being moved. Does that make sense? So what is velocity anyway? We could say another word that we could use is speed. Right, so how would we write, what are the units that we use for velocity? What, pardon? Okay, we could use meters per second. When we say meters per second, what are we referring to? Yeah, we're talking about how fast. What word could we use to describe what this is? We learned about it, did it in the math you need. Which is it's a rate. It's a rate, right? It's a rate. So we're looking for a rate. So we could have meters per second. Now you guys, how'd you guys get here today?
Miles per hour.
You drove, so you went miles per hour. Oops. Now meters per second is how we often report stream velocity. What's the imperial units? Because remember, we don't use English units because even English don't use them, right?
Yard
So-
for feet, yard.
We could use yards. Actually, when we're doing that, we usually use yards per hour.
Yeah.
But we would do more like feet per second. Now remember, you guys have math you need that's due tonight, right?
Yes.
You got topographic maps and unit conversions. Make sure you get them done. And very important for next week, I'll remind you that. Next week when we do the lab, if you haven't done the math you need, and you sit down in that lab is going to be very, very hard for you. So we don't want that to happen. So we've got meters per second and we have feet per second, which is generally how we measure the velocity of a stream. So if we think about a low velocity stream, what kind of sediment is that going to be able to pick up?
Not a lot.
No, let's
Small.
think back to our sedimentary rocks and our size fraction. Remember we had that grain size chart.
Very
What
small.
size do you
Fine
think?
grain.
Sand? We're talking really low velocity. Do you understand?
Fine, super fine things.
Yeah, we could maybe move the very finest grain. Remember that grain size comparator we're using? Some of those fine grains were really small. What's smaller than fine grain sand?
Silk and clay.
Silt and clay. Remember with clay, we have clay minerals that we've been talking about, and we have clay size. It's one of those confusing things. Right now we're talking about size. Now what minerals are typically clay size though?
Clay.
Clay minerals. So it's kind of one of those confusing things that we have. So a low velocity stream is only going to be moving these things. Right?
Well, it'll move debris too.
Well, yeah, there could be garbage that can float along, that can always happen. But we're thinking about natural products, geologic products. We're going to mostly be moving these guys. How about high velocity? How would you recognize if a stream was high velocity?
Rapids.
You might see rapids.
Like flooding water.
Waterfall would be great if that's how we get those huge holes at the bottom of the waterfall, right? That's how we get those pools. Now, when would we have high velocity stream? We might see it near the source, right? Because we've got, a stream has two primary parts. It has a source and what's the other end? At the other end?
Delta.
That we have a delta that is formed at the end. That's the sedimentary body. What is this? The stream when it exits into another body of water? What would we refer that to? It's a geographic term. Mouth. So near the headwaters or the source, we'd expect fairly high velocity. Why? Yeah, why does it have more kinetic energy? That's why we see the high velocity has more kinetic energy. But where did it get from? What's that? Not the altitude, but what do we, when we get high up, what do we experience?
Gravity.
Because why is gravity? What moves all streams? Gravity. They're all gravity driven, right? So if we want to move something that's driven by gravity, we want to move it faster. How do we do that? We increase the slope, right? So if we think about the beginning of a stream, what is our slope going to be? Flat or kind of higher? It's going to be higher, right? How about you get near the coast? What do we expect? Yeah, when you drive towards Galveston, do you see any hills? Do you see anything that even like gives the hint that it might go up or down? The on-ramp? Well, yeah. That doesn't really count. So high velocity stream can move very large particles, can move anything from boulders down, right? So it can move anything from boulders to clay. Now, how big is the smallest boulder you're going to get? What could be used as the basketball size, right? Now, do you think a stream is going to be able to move a house-sized boulder that fell off the mountain into the stream? No. Probably not. Probably not. Although, what is one thing that you're supposed to take out of this class with respect to water? It always wins in the end. So even if it can't actually move that boulder, what's it likely to do to the boulder?
Erode it down.
Break it down into small abrasion, which is a type of mechanical weathering, right? So we've got high velocity stream can move boulders through clay. When is it going to be at its highest velocity? Any stream can be anything from a fairly low, for its own conditions, right? It can be fairly low velocity, and it can be very high velocity. When is it going to be high velocity? Well, for a particular spot, yes. Higher slope is going to help us. So actually, velocity is one factor, and we can actually add the next one. Yeah, but what if we talk about it just one particular spot? We come there one day, it's low flow, and we come there another day, it's high flow. What's going to cause
Rainfall.
Right, if we're looking at flood stage. So gradient is one factor. Now what, everybody know what gradient is? What's another name for gradient? Slope, essentially. Now you guys all know slope, right? You've covered that in math probably since what? You were in elementary school maybe? Maybe middle school, somewhere in there. What? How do you figure out slope?
Rise over run.
Okay, everybody knows that, right? Oops. Now, you calculate it, right, by rise over run. We're looking for the slope, calculate the rise, we find out the rise and the run, and we can calculate our slope. What would we call that? We're doing gradient, and we're applying this to the real world, no longer just a math class. What would we call this? Altitude, or what's another word for altitude when you're talking about? Elevation. So we would have elevation. And we find out the elevation of this point, right? And the elevation of the starting point. And that would give us our change there. And what would we call this one? Distance. What units do we typically use for elevation? Feet. How about distance?
Depends on how far.
Well, if we're thinking like we're going from point A to point B at some distance.
Miles.
Now that's our imperial units. What if we were doing metric?
Kilometers.
We probably do kilometers, right?
I'll say
Yeah. So for that would be kilometers. Elevation we would use meters. Yeah. So we can either, but see, we don't report it with no units. This is one of the things you absolutely have to understand. Units matter. What happened with the Mars probe when they screwed up the units? They used different. Yeah, somebody was using metric and somebody was using imperial, and 180 miles per hour is very different than 180 meters per second. Right? They're very different. So units matter. You must keep the units. When you're working with any of these problems, you must keep the units. Do not drop them. So if we're doing in imperial units, we have feet per mile. If we're doing metric, it's meters per kilometer. We do not put them in the same unit. What is another word for this that we can use to describe what this is? Similar to what we did with velocity. A rate. It's another rate. That's all it is. We're saying about how much, over a certain distance, how much the elevation is changing. What's the rate of change of elevation? So we have velocity and gradient are going to affect. The next thing that can affect all of these is discharge. So what is discharge? We know? Right, it's the amount of water in the stream. And what we're looking at is if you're standing there at the stream and you're watching the water go by, how much water is passing you every second? And we do that in cubic feet per second, because how do you figure out volume? Sometimes we can figure out volume by weight if we know if we want to use weight to figure out volume, what do we have to know? Density. Pardon? No, you're right. You're right. What were you going to say?
Length times width times height.
Right. So length times width times height. If we're doing it in feet, our units will be what? Cubic feet. So discharge, and we use it as Q. I'm not sure why we use discharge as Q, but it is. Discharge equals WdV. Now, next question is, what are W, D, and V?
With
Water
depth.
distance rates.
Width times depth. You guys are quick this morning. Velocity. So what's our units for width? In imperial. Let's start imperial. Feet. Times depth. What are we going to do it in? Feet. And our velocity of the stream?
Feet per second.
And that would give us what units?
Cubic
Cubic feet per second. So that's how we get our units. This is because if I thought that I had to divide something and I flipped one of these, I'd get really bizarre units, wouldn't I? So when you go through it, if you don't end up with the units that you started with, you have a mistake somewhere. And that's what I use. When I'm trying to do a unit conversion of some sort, I write my units at the end, and that is going to give me a clue that I put all the ratios in the right way. The right one in the denominator and the right one in the numerator, and so on. So if we have an increased discharge, what's likely to change? We could get the velocity to change, but that's kind of a, right, the kind of velocity changes because the width changes and the depth changes, right? Well, maybe the depth or the width doesn't change. If it's a really steep-sided stream valley, is the width going to change? What if it's like this? Yeah, you guys, just recently, it rained a lot, right? Did you guys cross any streams? What did you notice about the streams? There was a lot more water, they were a lot deeper, and they were a lot wider. So, anytime that we change one of those two, we're going to affect this one, aren't we? If we hold this one constant, if we change this one, we can change everything. But one of the things that we run into, especially when we mess around with streams, because we like to do that a lot, don't we? We change where they're going, we force them to stay where they are, we do all kinds of different things to streams to make it work for us. Now if I have the same discharge, if discharge doesn't change, so Q is held constant, but we're coming up on a bridge, our stream's going along, and it comes up on a bridge. Am I going to want that stream to be able to do whatever it wants around that bridge?
No.
Potentially no, right? So I might narrow the stream. So if I decrease this, what's going to happen to my other two variables? Remember, this hasn't changed. I didn't add or subtract more water. They're going to increase, right? So if I change depth, and I'm going to actually decrease it, or sorry, no, not that one. We see this both in natural and in man-made situations. Sometimes as the stream is traveling along, it hits a very resistant rock, one that is not particularly cooperative when it comes to mechanical or chemical weathering. But then in another, it could be granite, exactly. And another area might be really easy to weather. It might be limestone, or it might be shale, which weathers really very easily. So it may make a very wide, shallow stream. And what's my velocity going to be in that case? It'll be lower. And then it comes to an area where it's really resistant to weathering and it's going to narrow up. And when it does that, we get this situation, right? So we can see that in an individual stream where it spreads out, it slows down, and when it gets narrow, it is going to increase.
Kind of like water pressure in your water hose, right?
Yeah, if you change the diameter of the hose, it's
Right.
going to change the velocity of the water coming out. Exactly. So we can do that, and streams can do that. Now, why does that happen? So we look at it mathematically, and we can see the obvious factors. But if we look at two streams, I'm going to draw two identical streams. So we're going to pretend they're identical because I doubt I'll draw them exactly. They're going to have the identical cross-sectional area. Everybody understand what I mean by that? So that means these streams are going to hold the same amount of water. Which one, A or B, is going to have the higher velocity? Okay, why?
It's narrow.
But by mathematically, we see it's narrower, so it's going to have to be faster. But why? There is physics.
There's
reason.
less surface area.
Exactly. There's less surface area, which means what?
Less resistance.
Less resistance. There's less water in contact with the stream channel below. What about this one?
It's more spread out.
It's more spread out, so there's more water in contact, which means what goes up? Friction goes up, right? So this one has greater friction, the water slows down. This one has less friction, the water goes up. Now, the next interesting thing is where within this is the fastest moving water? Why the middle?
It's
Yeah.
not environmental, it's not the size, it's not the bottom.
Right, because what happens to this water up here? What's it touching?
Wind, air.
Touching air. We don't think of that, right? We think of there as being nothing. There's like nothing in this room, right? In this space, there's nothing. But if there was really nothing, how would you guys be feeling? Not too good, right? So the fastest water is actually right about in here. It's not at the top, and as far as you can get from the sides is the fastest water. In this case, it would be the same sort of thing. It would be there. Lower below the surface, but not near the sides. So we see that in streams. Actually, one of the things, remember, if you're thinking back to when we were talking about volcanoes, remember when they said in that video, they said where it's narrow, the lava's moving really fast, but when it gets spread out over an area, it slows down, and so do pyroclastic flows. It doesn't matter if we're talking about water, or we're talking about lava, or we're talking about any fluid, it's going to work this way. Exact same thing. So it kind of all plays together. Now there's one more factor of a stream that's going to affect erosion and deposition. So we've covered velocity, so that's the speed of the water. We've covered gradient, which is the slope of the stream bed. We've covered discharge, which is the amount of water in a stream that moves by a given point. What's one more thing you can think about a stream, characteristic of a stream that maybe could affect how quickly or how well the water moves on the ground?
Where it ends up, how well it disperses in.
What do you mean?
Like if it's bottom, if it's empty into something that's not really fast, it's not gonna have anywhere to go with the water.
That's true, but think about the stream itself.
Wouldn't it be the amount, because if there's just a little bit, it's not gonna move very fast?
A little bit of water, you mean?
Yeah.
Yeah, that goes with discharge. But think of one more thing that's not gradient, discharge, or velocity. Well, shape we got kind of here, but you're right. No, if it's meandering, we'll come back to that. Meanders are actually the result of velocity.
Direction.
And very pardon?
Direction.
No, no.
Stuff in the stream.
Sorry?
Plant life in the stream.
Plant life can help, but if we think non-organic material, because most streams don't have a lot of plant life.
Rocks.
Rocks, exactly. If this bottom of the stream is covered with rocks, how fast is the water going to move? Is it going to be able to flow really fast and easily, or is it going to have to like move around the rocks and stuff?
Depends how big the rocks are.
It's going to move around. It's going to. You ever watch a stream in a rapid? Some of the water actually goes uphill, right? Because it hits the rock and bounces back and so on and so on. So I kind of covered this one. We're all kind of out of order here. What, 4? The channel shape and roughness. That we kind of covered channel shape over there already with discharge. But the other is roughness. So channel shape, we can put that under there, and then so if we put rocks in the stream bed, and if we have a bunch of rocks, is that going to be a smooth channel or rough?
Rough.
Rough. How would we create a smooth channel bottom? What kind of a sediment would we want in the bottom?
Clay.
Sand and clay. So we have a smooth bottom. Smooth bottom, the water can flow faster than if we have a rough bottom. What's that word we use to describe when something can move easily over a surface? That's resistance to flow of water. We want resistance to flow of something over something else. Starts with an F. Friction. So we have greater friction here. Lower friction here, right? So So essentially that's all, and that comes back to here too. So essentially channel shape and roughness is a factor of friction. High friction, we're gonna have lower flow. Low friction, we'll have higher flow. Now, why do streams meander? Taking all of these factors into consideration, how many of you have walked up a mountain? Or down a mountain, either way. How do you typically walk up a mountain? Very slowly? Yeah. One foot in front of the other, right?
Like that.
Why do you meander?
Because you're taking the easiest path to get up.
Why is it easier?
Because of the rocks, the boulders, the trees, the forest, everything.
You might be going around stuff, but one of the things that you're avoiding by going like this, what do they call that when a road does this? Switchbacks. Why would you have switchbacks? Why not just go straight up the mountain? It's a lot less. Yeah, it decreases the slope, right? You know, if you go straight up, that's a lot more effort than if you just kind of meander your way up on switchbacks. If you ever try to take your car up on a really steep hill, you can listen to the engine and see how much it's straining, and you know it would prefer to do switchbacks. So essentially, this is the same thing. Every single stream has a point of equilibrium. Everything in nature is always looking for equilibrium, and anytime that we get it out, that it gets out of balance, something happens to try to swing it back towards equilibrium. Nature likes balance. How come? Is it just egalitarian that way? It likes to be friendly and equal, and what's it want balance? Sometimes it helps things survive, but why? If you're, sorry?
Easier.
It's easier, which means you have a lower what? Starts with E. When something's easier, you expend less effort or less
Energy.
energy. So anytime we're looking for low energy. So when a stream is meandering, it has less energy than if it's running straight down, pell-mell down the hill, right? Well, why would a stream want to be in balance? And I say want to. Does it really actually sit there and think, I'd really like to be in balance today? Doesn't do that, right? No, it doesn't. It has no ability to think whatsoever. But it moves towards balance because when things are out of balance, if I have a stream moving really fast down the mountain, what's it going to do? It's going to erode, right? And there's something funny about when water moves around a bend. What does it do?
It's a whirlpool.
It does. It actually, there's little vortexes that come as it comes through. But when water is moving in a straight line here, does it automatically bend itself?
No,
What
it's the
bends
wall.
it? What causes the water to bend?
The bank.
The bank, right? It's going to hit the bank. What's that rule that says things in until so what's the outside force here? The bank. So it's hitting this wall and then bending around. You guys ever play that game where you all hold hands and you spin around in a circle? Ever did that?
Yeah, me too.
The person on the end is trying to run really fast because they can't. They end up falling. That always happens. So water flowing here hits that bend and is forced to swing around.
So that's how they become meandering.
Pardon?
That's how they get meandering.
Right, because when it hits here, it erodes. And then it's forced this way, and what's it going to do to this bank? It's going to erode that one, and so on and so on. So if we were to walk across here, say from point A to A prime, if I were to draw that, where would the deepest part of the channel be?
On the right.
Right, so if I were to draw this cross section, it would look kind of like that, right? How about if I draw it here?
It's gonna be equal pretty much.
It's pretty close to even, right? If I can draw these, but they look that way. How about this one over here? it's to the left there?
Yeah.
So the deepest part of the channel is not going to stay in the same place. Why does it get deeper here?
All the water is going into the bank.
Yeah, there's something funny that happens. When water is going around the bend, it tends to rotate. It tends to rotate as it comes around here. There's a little bit of a vortex that occurs. When you stir up who likes sweet tea? Now, do you always get sweet tea, or do you get that unsweetened, you gotta put sugar in? Yeah, sometimes you do that. So you get lucky that I always have that. If you stir up, okay, before we get to that, you guys heard of centrifugal force, right? What is centrifugal force? Sorry? Something with a circle, yes, something with a circle. What?
Concentration, aim, momentum.
When the circle is rotating, it pushes the edge.
Yeah, pushes to the outside of the edge. How do you know, does that when have you noticed that you get pushed to the outside of the edge when you're going in a circle? Pardon? Yeah, when you're making a car, as a driver, you don't notice it so much because you're holding the steering wheel, right? You can kind of control. But when you're sitting in that passenger side, what happens to you? Depending how fast you're going around the corner, right? Did you ever go on those tilt-a-whirl rides where you go, you go with your sibling, and the best thing is when you put your younger sibling on the outside so that when you're going around, you squish them. Centrifugal force actually doesn't exist. There's no such thing. There's centripetal force, which is towards the center. So we use that. This is one of those things where we kind of teach you wrong, unfortunately, early on in your younger years, because we have to simplify it. And by simplifying it, we often introduce misconceptions. Which means when you come here, then we have to unlearn and relearn, which is, I could go on about my opinion on that, but we don't have time. So we talk about it because if I put a bucket on a string and and fill it up with water and I swing it, does the water come out? Who's right, not until I go fast enough. You go on the super duper looper type roller coaster rides, you guys all fall out? No, you get kind of glued to it. You do have a seatbelt on, of course, but even if you didn't have that, if it was going fast enough, would you fall out? No. But that's not a force. Anybody know what it is?
It's acceleration.
Yeah, it's a change in acceleration. Because remember, we looked at that water, the water's going in a straight line, and then what happens? It hits the bank and it has to turn. When you are in a car, you're going 40 miles, let's say you're driving 40 miles an hour, you're on a straight road, and then there's a bend. You're doing what? You're going straight forward, right? And acceleration has two components. It has velocity and it has a direction, right? There's a change. There's a few other things in there. So when you go and you turn, what's turning you? What's causing you to turn and go around that bend? Well, the car is turning, but you're the passenger. You're going in a straight line. Remember we said that everything goes in a straight line unless acted upon by an outside force? What's the outside force?
You are.
The car. You're running into the door, right? Do you ever drive and you have the air conditioning, you're driving and everything's great, and you turn a corner and you just blast of cold air? Pay attention, you should notice it. That cold air is moving in one direction, the car turns, and now it's still going in that direction until it hits the windows. Or you, or whatever it hits. So centrifugal force is actually a way to describe the change in the acceleration around the curve. So it's not actually a real force. The force is towards the center. Now we talked about going in a circle. Let me get one demonstration here. Okay. Water and some sediment. I'm going to...
He's gonna go from outside.
I guess we go the outside, some say the outside, some say the inside, and the survey says... Where'd it go?
It's in
It goes to the middle. That is centripetal force. There are little vortexes that occur. When you have a vortex, the sediment goes to the center. So when the water goes around, sediment is moved this way. So we end up with a lot of sediment on that side. So the sediment is eroded here, and then it is moved towards the center, producing a nice beach. Anybody ever go to a stream and there's a nice little beach there on the inside bend of the stream? So this little deposit here is called point bar. Any deposit of sand in a stream or sediment, doesn't matter what kind of sediment, is a bar. This one's a point bar because it's on the edge. This side is called the cut bank. Why do you think it's called the cut bank? It's getting cut, right? If we were to go to a stream, and what do you think we'd notice if it was being eroded? What would you expect to see if that bank was eroded? You might see a cliff or a high bank of some sort. What else might you see?
Roots.
Roots, and even what's attached to those roots?
Trees falling down.
Trees falling in, all right? If you take away all the sediment that's holding the tree up, the tree's going to do what? It's going to fall in. So we expect to see that on this side. What would we, well, look at here, see the slope? This would get all filled up with sediment, and so we'd have a nice gradual slope heading towards the center. Now, when we go to Jesse Jones Park this Friday, if the water has not, it's supposed to rain again today, right? If the water level's not too high, we'll be able to go and stand on one of the point bars. And we'll be able to see it very, very easily. If the water's too high, it might not be there. One of the things that happens sometimes during flood stage is the point bars can be completely wiped clean and sent downstream. So these become eliminated on all sides. Now, if this is eroding and this is depositing, what's going to happen if we were to come back to the stream, say, in 30 years? Would it look exactly like this? What would it look like? So this meander would get wider, and then it would go this way, right? And it would keep going down. Can you think of any potential problems that might present in the future? Yeah, a bridge would be bad. If you were to build a bridge on that stream, where would you think?
At point B.
Yeah, why point B?
It's less erosion.
It's going to have less erosion, so less risk of injuring the bridge. But what do we often use stream? In fact, we use Spring Creek as one of these. What are streams often used as? We can put dams on them, but think political. Yeah, they're often used to set boundaries. They can be used to set political boundaries. And what's the boundary in Texas between Mexico and the United States?
Rio Grande.
The Rio Grande. Between Harris County and Montgomery County is
Spring Creek.
Spring Creek. So when I use a stream as a boundary, depending on the situation, what could you imagine occurring?
Boundaries change.
The boundary's going to move.
The volume of the county, the size of the
Yeah, it
county.
might change a little bit. Now, most of the time, if it's over a long enough distance, it kind of comes out in the wash. Like the Mississippi River has abandoned over 600 miles of channel, but yet it's no shorter than it was in the beginning. Because if I get rid of a meander here, I'm probably going to create a new one somewhere else over time. But if I have a stream here that keeps meandering, where's my pen at the back? Here's my meandering stream. It starts out like this, and we have a property owner over here that says that their property is from the road to back 500 yards or so. Or no, let's do it to the stream. So that's the property, from the road to the stream. The stream is its property line. Now I've got another guy over here, and And his says it is, say, from the road's out here. Go right through his house there. From the road back 500 feet. So this is in another county or another state, whatever. And they draw, this is how they write up their deed. And this one over here is more survey conscious and pays more attention. So the person buys it, and then 30 years later, what might happen?
400.
Stream's going to move. And instead of being narrow, it's a different color. Now my stream looks like this. So where's this guy's property line? The stream, right here. Where's this guy's property line? 500 feet back. What does that create? A disputed land. It's actually happened before where a farmer moves his fence over there and this guy goes, hey, that's my property, get your fence off my property. He goes, nope, mine says 500 feet back from the road, that's my property. So then you end up with issues. So sometimes when you're dealing with streams, those can become a problem. Now, what we try to do then is we try to prevent this through erosion control measures. Have you ever seen on a stream any kind of erosion control measure?
Yeah.
What have you seen?
Okay.
Concrete, the rocks, pile.
Yeah, they put, every see in a stream they've got one bend concreted. If you travel on 1960 near 290, you cross over, there's a little drainage. I'm not sure if there's actually, I think there's a stream in it, but it's one of those things where it might just be a drainage. And what they've done is they lined this bend with concrete, trying to armor this bend so it
That's
doesn't
what those
get
little
away.
interlocking concrete things are they're putting on everything now, right?
Yeah.
It's not, they don't pour the concrete, they just use those.
Sometimes they can use those, I forget what they're called, but yes, they form a mosaic and they can do that. Sometimes they'll put piles of rocks to try to protect the, because the rocks wouldn't be moved by the stream because they're too big for that particular stream, and it would protect the sediment underneath so it couldn't be moved. Now if I concrete this side, what am I going to do to the velocity of the stream? Because I made it smooth. I'm going to increase it. Now this guy down here doesn't have his concreted. What's going to happen?
It's gonna wear down faster.
It's going to wear down faster. So I've taken the erosion potential here and I've added it over here. So what's this guy going to do? I armor it, and then what happens? I just moved the problem. Have I solved the problem? I just moved it. I sent it off to my neighbor. So mine is fine for now. Remember, what happens? What does water always do? So I can, maybe for the life of my mortgage, this doesn't change. But at some point, there's going to be a big enough storm that creates high enough velocity water that it's going to rip that cement up. It's going to go underneath it. It's going to tear it all up, and that'll be the end of it. You think you can build something that can withstand anything that water can throw at it? You can't. And that's when we get in trouble. We always have to remember water always wins, and if we live under that mantra, we'll probably be okay. If you try to battle water straight on, you will lose at some point. Somewhere along the line, it may take a while, but you will lose. It's not a matter of if, it's a matter of when. So streams are naturally migrate. Now sometimes we end up with a stream that does this. Can you foresee something happening here?
It's gonna become a lake.
It'll break through right there and it'll cut this off.
As soon as it floods, it's gonna go.
Exactly. As soon as it floods, it can cut through here. So what we'll end up with is this will go straight through here and it'll cut off
So water will just completely stop flowing through the other part?
Except perhaps during flood stage. That's the only time we might get water into here. And of course, when it rains, there'll be runoff that goes in here. Now, anybody know what this is called?
Extinct?
It is a name for it. Starts with, oh, what does this look like? If I took it here and I held it like this.
Horseshoe.
It does look like a horseshoe, but think bigger than a horseshoe. Made out of leather.
Stop.
A yoke, oxbow.
Oxbow.
Yeah.
You know, it's hard for us to remember these things because, of course, how many of you guys have ox? Anybody? Have you traveled in a covered wagon pulled by a pair of ox recently?
Nah.
Yeah, no. So this looks kind of like an oxbow. Of course, it was named when the oxbows were in fact utilized. So sometimes it's always one of the interesting things about names is where it come from. So this is an oxbow lake. We have lots of them. Eventually, this actually ceases to be a lake. Because as the runoff from the land drains into the lake, what does that runoff probably carry? Sediment. So what's it going to do to this?
Take it up.
Fill it in. It'll fill it in. It becomes a marsh for a while, and then it's not there anymore. In fact, if you fly over the Mississippi River, anybody ever flown over the Mississippi River? Actually, any large enough river that you can see from the air,
Yep.
you can actually see oxbow lakes and meander scars. When they fill in, they're called meander scars. The next time when we look, I'll get out topographic maps, and we'll actually be able to see some of those meander scars on the maps. They're quite interesting, but you can see how much the Mississippi River or various rivers have changed. And then when we go to Jesse Jones Park, we're actually going to walk past one of those meander scars that used to be spring.